Hi guys, my name is Neva and this is my Chem 6BL video project. Today I will be teaching you how to make kombucha and the chemistry behind kombucha. So first off is the recipe. We are going to have 3 tablespoons of black tea, loose leaf, and you're going to add it to a cotton bag or a tea strainer. And you are going to mix this with 4 cups of boiling water, and we are going to let that steep for 5 to 7 minutes. Alrighty, so now that the tea has been steeping for 7 minutes, we are going to remove the bag and then add 200 grams of raw cane sugar, or 1 cup, and we are going to mix that until it dissolves. Now that all the sugar has dissolved, we are going to pour our new sweet tea mixture into a gallon jug. Now to this jug, we're going to add 8 cups of cold filtered water, and we're going to check the temperature after. And if it's not cold enough, you'll continue adding cold water. And then our last 2 cups. And then with a temperature stick, we're going to put this on the side of the jar and see what the temperature is. So we're going to check the temperature now. And it is about 78 or 76 degrees Fahrenheit. And as long as it's between the range 68 to 86 degrees Fahrenheit, you're all set to go. Next step. Alrighty, so now we're going to add the SCOBY. And the SCOBY is a symbiotic culture of bacteria and yeast. And it looks like this. It's kind of weird looking, but that's what makes everything happen. And I'll be explaining the chemistry of how that works later on. And then this is also some kombucha starter fluid, which is recommended in a first batch, just to make sure it occurs. And then we're going to mix that for a little bit and test the pH. So for the last step, we are going to check the pH to make sure it's acidic enough. We need a pH around 4.5 or below, and I'll explain why later on. So we are going to use the pipette to get some of our solution up and spread it on pH paper. And then we are going to compare this to our guide. So it looks like we have around 4.5, so we're ready to go. Cover the top with a linen cloth and rubber band, and then place it in a dark and dry place in your house for the next 14 days, and then we'll come back and check on it. So it is day 8 of the first fermentation, and unfortunately I'm going to have to stop here due to the deadline of the project, but as you can tell, there is a white thin biofilm-like layer on the top of the brew. And this is actually cellulose, and that is a good sign that the fermentation is occurring. So it might be on the sweeter side just because we're not doing the full 14 days, but that is okay. So I'm going to check the pH really quick and do a taste test as well. Alright, so I'm just going to dip this in there. And it is pretty yellow. So in comparison to this, I would say it's 3 or even less, so it's pretty acidic. And as far as taste, it was very sweet. So the last step is the second round of fermentation. And during the second round of fermentation, you can add flavoring. So I will be adding 1/4 cup of pomegranate juice with diced up strawberries to an airtight container like so. And once the juice is in there, you'll fill the rest of the bottle with the brew, leaving about an empty space of 1 inch at the very top. So what's happening on the chemical level? Making kombucha seems relatively simple, but the SCOBY is hard at work. SCOBY stands for symbiotic culture of bacteria and yeast. A SCOBY contains acetic acid bacteria, lactic acid bacteria, and yeast. The most common yeast organism in kombucha is Zygosaccharomyces, which is responsible for alcohol fermentation. As for the bacteria present, acetic acid bacterium Gluconoacidobacter is aerobic and uses alcohol to make acetic acid. Here's an overview of the reaction at hand. There are many different types of yeast and bacteria present, but these are found in the highest quantity. So to start off, in alcoholic fermentation, yeast produces invertase. Invertase catalyzes the hydrolysis of disaccharide sucrose by cleaving it into monomer units, glucose and fructose. Invertase cleaves the glycosidic linkages. With glucose and fructose newly formed, alcoholic fermentation continues, and glycolysis breaks down glucose into 2 pyruvate molecules. The first step releases carbon dioxide from pyruvate, which is converted to a 2-carbon compound, acetaldehyde. In the second step, acetaldehyde is reduced by NADH to ethanol. This regenerates the supply of NAD+ needed for the continuation of glycolysis. The conversion of pyruvate to acetaldehyde is monitored by the enzyme pyruvate decarboxylase. Here's the mechanism of the reaction using an abbreviated version of thiamine pyrophosphate. Thiamine pyrophosphate is a cofactor of pyruvate decarboxylase and acts as a nucleophile and attacks the most electrophilic carbonyl group of pyruvate. This is similar to the dihydropyridines experiment. The second carbonyl group is closer to an electronegative oxygen, therefore not as electron deficient. Carbon dioxide is released, which is why we see bubbles in kombucha tea. This is what makes the drink fizzy. Furthermore, the negatively charged oxygen pushes its lone pair to form a double bond and breaks the double bond to TPP in order to be released as acetaldehyde. Acetaldehyde is then simply converted to ethanol via an oxidation reduction reaction, gaining 2 hydrogens from NADH. If you have ever bought kombucha from the store, there is a warning that the tea does contain some alcohol, even though it is not considered an alcoholic beverage. The acetic acid bacteria from the SCOBY oxidize ethanol to acetic acid, causing that vinegar taste in kombucha, but sometimes there's a little bit of ethanol still in solution. Acetic acid bacteria converts ethanol to acetaldehyde and then to acetic acid using alcohol dehydrogenase. So when you drink kombucha, you aren't drinking alcohol, even though it's produced during fermentation. The last thing I wanted to mention again that different bacteria strains can produce different organic acids, such as lactic acid. As you can tell, a lot of acids are being produced, which is why we saw the pH drop even more after fermentation. The cellulose layer we saw on top of the kombucha was formed by the bacteria cells. The process includes the synthesis of uridine diphosphoglucose, which is the cellulose precursor. The acetic acid bacteria can then polymerize glucose into beta-1,4-glucan chains, creating fibrils. The biofilm will continue to grow and thicken throughout fermentation.